Example 4. The tank in the figure contains water to a depth of 3 meters. Determine the resultant force and its point of application that the water pressure creates on the sides A, B, C, D of the tank and also on its bottom. Now, with the concept of rectangular prism, right, that we can do the analysis of our water pressure in terms of the original definition of pressure, which is force over area, right? If pressure is equal to force over area. And if you want to express this in terms of force only, so this becomes F is equal to pressure times area. So if only we knew the amount of pressure that our fluid exerts, we can calculate the resultant force on a certain over a certain area, right? Okay, so but we do know that as we increase as we go deeper, our pressure also increases. And the maximum pressure of our fluid is equivalent to the entire column of that fluid, right? The maximum pressure that our column of fluid exerts. So therefore, the total height. So for this case, that is at the very bottom of our tank, which is 3 meters deep from the surface. But before we go on with our analysis, let us write first the given. We have our depth. Let us have our depth is equal to 3 meters, right? And our fluid is water. So the density of our water is equal to 1,000 kilograms per cubic meter. What is required is the resultant F sub R at the side, which is side A, B, C, D, and at the bottom. Okay. So actually, this is very straightforward, but what is needed here is some sort of analysis into how are we going to solve for our resultant force. Okay, we know that the pressure that our fluid exerts is equal to, can be solved through using this formula. Pressure is equal to our specific weight times our height, right? Meaning the amount of pressure that a column of our fluid exerts to our tank or to our object. And this is also equal to density times acceleration due to gravity times our h. And this is 1,000 kilogram per cubic meter times acceleration due to gravity. So that's 9.81 meter per second squared. And then this is our height, the column of our fluid, and that is 3 meters. So kilogram meter per second squared, that is Newton. Meter, and we have cubic meter here, so it cancels. What is left is just meter squared. So that's Newton per meter squared, and that is in Pascal, right? Which is a unit of pressure. So P is equal to 1000 times 9.81 times 3. So that is 29,430 Pascal or Newton per meter squared. So we'll just use Newton per meter squared because we will still derive our F sub, the value for our S sub R, which is in Newton. Now, like I said, we go back with this formula. F is equal to P times the area, right? Okay. And for our uh at the bottom, okay, at the bottom, okay. So this is F sub R at the bottom is equal to P times area at the bottom. Now this area is the kind of uh how our pressure is distributed over that area. Okay, so for the pressure distribution at the very bottom, it looks like, say, this is our bottom part of the tank. Pressure is evenly distributed. So if we try to look at it sideways, it kind of creates a rectangle. So therefore, the area that we will be using is base times height, or the area of our rectangle. And our base would be the values that we'll be using is 2 and 1.5. So this is pressure, which is 29,430 times the area, which is 2 times 1.5. So our F sub R at the bottom is equal to times 2 times 1.5, and that is 88,290 Newton. This is the force, the resultant force that our fluid exerts at the bottom. Now at the side, which is A, B, C, D. So if you try to, if you make a illustration just like this one for our side, for just like this one, it will look like if side, okay, A, B, C, D. And we know that as we go deeper, the pressure at the surface is zero, but it increases as we go deeper. So therefore, it kind of look like a triangular figure for our side pressure here, kind of like this one, right? Yeah. And the maximum pressure, this one, at the 29,430 Newton per meter squared pressure is at the very bottom. So therefore, for our F sub R at the sides, that is equal to the pressure, which is 29,430 times the area, which is, for this case, it's triangular area. So that is 1/2. Our base would be 2 meters because this side is ABC. So this would be its base, and our 3 meter is our height. So 2 times 3, 1/2, 2 times 3. So our resultant force at the side is equal to 2 times 3 divide 2 times 29,430 is equal to 88,290 Newton at the side. Okay, so for its location at the bottom, since our uh, structure or the plate is rectangular, right? And the pressure is evenly distributed at the bottom. So therefore, uh, the point where our resultant force acts is at the centroid of our structure, which is 1/2 of 1.5 and 1/2 of 2, which is 1. So for this at the bottom, let us say let us have this as if we are to make a XYZ coordinate here. So let us say this is our Z, this is our X, and this is our Y. Okay, just to show the location. So for the bottom, we will be using X and Y. So XP, YP. XP is equal to 1 and YP is equal to 1/2 of 0.5, that is 1 meter rather, and YP is 0.5 meters. Now for the side, so that would be XP again, and still 1 meter, right? Is 1/2 here, half, and then we know that the the pressure here creates a triangular loading. So if we view it sideways, it will look like this one, right? So we have either from the bottom, that is 1/3, and from the top, that is 2/3. So if we are to measure it from the bottom, XP is equal to 1 meter and ZP, sorry, this should be ZP is equal to, uh, our formula, we will be using the formula 1/3 times the entire height, which is 3. So our ZP is equal to 1 meter from the bottom. This is X sub P and Z sub P. Okay, so this is the locations of our resultant forces using the rectangular prism principle.